Good afternoon, student 4022. Uh, Today there was some questions about how to set up LEDs in parallel. Seems like you got a pretty good idea of how to set LED in series, but there's some confusion when I work with LEDs in parallel. And this is the story. Let's say that we have a 9-volt batteries. Let's put here kind of a breadboard so everything looks well aligned. And so let's say that I power these. Let's see. And when I power this, the positive rail right through here. All right, so let's change some of the colors. Red and black. That's it. So let's work with one particular LED. Let's bring the red LED here, and let's say that I'm gonna power these LEDs. Let's put that LED right. I thought to put the LED between this side and this side, but I think it's good enough to put the LED on what I will call. Let's start this and let's put it on one side only. Actually, let's do that. Looks a lot better. So I'm gonna delete this one, and so let's say, for the sake of the argument, I'm gonna bring a resistor. So that resistor will be the main one, and this is what I will do. Let me bring also an instrument that is going to be used to measure the amount of current that is used from escape. So we will use this one in series. Here we go. And let's see. So this one will go right to negative, and this one will come right here to negative as well. So now let's see how this works. It's kind of weird the way it is. So let me redo this because that will not go there. There we go. So let's see. If I start here, go through the resistor, go right here, and this is the power, but it's power that need to go to this here, to this rail here. So that power need to go to here. There we go. And now what I need is something like an instrument or a device. Let's say that I have this LED here, and that LED has to be protected by this resistor because we're gonna put a bunch of LEDs in parallel. Maybe this circuit is not that clear how this will look like, but this is the negative, and that goes right here, and now the positive is this one, so that goes right here. If I have the right this resistor is about 1 kilo ohms, should work to power this LED. Let's start. There we go. So I'm consuming about 7.04 milliamp. Let's stop and let's put the right color here so everybody start to understand what I'm doing. Black. Let's set this red, and this one is also red because I'm bringing the power from this also to red. There we go. Now, so this here is black, and I'm powering this. That's it. So I can put a bunch of LEDs, and actually let's copy this one. I'm gonna copy and paste. Gonna put it right here. Oops, there we go. Copy and paste. And this is what's happening. So I'm sharing, since they are all the same voltage, and this is what I'm gonna do. They have to be to the here, this leg here, and this is the anode leg that need to go to the positive. So this go right here, and this also go from here to here. So I have that completed, and that should power the 3 LEDs. Start. There we go. So let's see how this works. There's amount, each of these LED is taking an X amount of current based on the total amount of current that I allow through this resistor. So depending on how much current you want through all of them, then you have to make the following. It's an exercise where you take 9 volts, which is the source, and you subtract the voltage of one of these LED that is in parallel, and when you do that, then you need to decide how much current will go through each of these one, and you will add up. So the current is being added up, and that will kind of will get you the size of the resistor. So let me do this in 1 second. Let's see if I can write somewhere here. Well, actually, add another LEDs as we talk about it, and we do the math in a second. So I keep adding LED, and one thing that I could do is add an instrument to see what is the amount of current going through one LED, at least one LED. So let's use one LED for testing, and so let's see the last one. So I'm gonna be adding this right here to the ground, and this one goes to the positive, and this one goes to ground. Actually, this is the LED that I'm gonna test. Let's see how I do the circuit here. So this is positive, and so this is ground. I think that ground can go right here. Now this one is positive, but this positive will go to the instrument, so I can read the current in series. So let's change this to amperage, and let's come with this one down, and this one will come down here. So I'm powering this last LED right through. Not that I'm powering, I'm sorry, I'm adding an instrument in series to measure the current that this LED consume. And so all the LED are the same values. Okay, so let's do that. Start simulation, and that tells you that each LED is consuming around 1.43 each one. So if you add up all that, I mean 1, 2, 3, 4, 5 times 1.43, that provides you that 7.15 milliamps. So if I take this resistor and I, instead of 1 kilo ohms, I can change it right in, at a fly. Obviously they are all blow up just because I put 1 ohms. So let's change the 1 ohm and put a value that makes sense. Let's say 100 ohms. When I put 100 ohms, as you can see, through these LEDs, which I see in parallel with this, in parallel with this, in parallel with this, in parallel with this, I'm pulling about 13.7 milliamps. 1, 2, 3, 4, 5. If I add another LED, let's see what happens. Stop simulation, and oops, stop. There we go. And now let's stop here. Let's copy this one and add another one. So this will go to ground, and this will go to positive. There we go. I should change this so that everybody looks the same. There we go. Let's see if I can do that. There we go. All right. So this allows me to measure the amount of current. The amount of current should get reduced as I add more LED. Let's see what happens. Start simulation. So yes, 11.5. If you keep adding more LEDs, the amount of milliamp through each single LED will get reduced and reduced and reduced. And so, like for example, stop simulation. Let's add one more. Actually, so it's 11.5. Good. 11.5. Let's see what happens if I add another more. Again, this goes to negative, and this goes to positive. Let's see what happened with the 11.5. Start simulation. Drop to 9.88. See? And I have 1, 2, 3, 4, 5, 6, 7. If you multiply 7 by 988, that gives you the 69.9, which is consumed through the whole circuit. So the question is how I get this value right, without messing with it. Can you hold for a second? So let's do a little bit of math and on this, so bear with me. Let's say that I have a battery right here and that I'm putting these LEDs like this, and they are in parallel. This is the symbol for the LEDs. And I keep adding more LEDs and so forth, right? So these are LEDs. And let's say that these LEDs are about 2 volts each. And there's a resistor right here with a value R that we've been told that we need to calculate that resistor so that we protect the LEDs so that they don't carry on with too many amps. Let's say that this is a 9-volt batteries as the Tinkercad example. So 1, 2, 3, let's add another one. So I add another one LED there. And let's say that for each parallel LEDs are going to run 1 milliamps. So it's going to be 1 milliamps here. But that's very tiny amount of current, 1 milliamp. But it's okay. I mean, you can set this value to at least less than 20 milliamps. That will be okay. So the amount of current that I need, or that is required through at least through this point here, is 4 milliamps. All right. So to calculate R, you're talking about how much current is going through the loop. So there's some part of the current some part go through here, another go right through here, and this one here we know that is 1 milliamp. So the calculation about how to do with this, when you think about it, so will be like sort of like a Kirchhoff type of analysis, where you will put, like for example, minus, there we go, minus 9 volts, which is starting from here, and this is positive, plus the amount of voltage drop through the resistor. That would be I, the current, time R. I know R. I mean, sorry, I know the amount of current because it's the sum of the current through each LEDs. So R is the unknown. So how about here? Now when you finish this, that will be plus the voltage drop right through that LED. That's about 2 volts. and that bring you right here to this side, so that will be the end. So basically what we have to do now is work in terms of R, our expression there, and that will be sort of like -9 and 2, that will be -7, so that -7 goes right here, so you end up with 7 divided by the value of the current. That will be 0.004. That's for the 4 milliamps. That will be 4 milliamps, and this is the value of R, which basically will be about, let's see, that's 7 divided by 0.004. That's ohms. So that is the size of this resistor here to have at least 1 milliamp going through the circuit. The LED will be not, they would not be illuminated enough, so better that probably the amount of current that you want to have through each LED is about 10 milliamp, and that will do very good. So you can redo this calculation for let's say 10 milliamps through each of them, so 10, 20, 30 and 40. So if I set 40 milliamps through all of them, meaning 10 milliamp here, 10 milliamp here, 10 milliamp here, and 10 milliamp here, that's 40 right here at this point. So when I go do the curve cut, we'll get with the same number, which is basically 7, but now divided by a larger current. That would be 0.040. So that the value there will be about, let's say, 175 ohms. 175 ohms. See, that's how easy you calculate the value of the resistor, a current limited resistor for protecting the LEDs. But again, you can keep adding LEDs and so forth, as long as the battery can provide that total amount of current as required per LED. The other important requirement is that the voltage drop has to be identical on each one, because if one of them has a higher or lower voltage drop, that will dominate the one that has the lower. Like for example, this is 1.7 and all of them are 2 volts, so this one is the one that actually will kick in. The other one will be like they're not there. So it's important that the voltage drop through each one be identical as possible for this circuit to work as as designed. All right, let's say that now we want to review a little bit the LEDs in series, and let's see how will that work. Like for example, let's say that we have, let's see if we can get this going. If we have a circuit like this, I'm going to be using the 9-volt batteries like in Tinkercad, so we relate to it. And let's say that we put our resistor right here, and then we put a bunch of LEDs in series. Let's say we put 4. Then we return back to our negative side. And this is R. So the current here go like this, similar to our other case when they are in parallel. So we're going to be doing, this is an 9-volt battery, and what we're going to be doing is calculating what should be the value of R for a given current on these LEDs. What is interesting, these LEDs could be potentially different voltage. The voltage drop of this one could be different from this one and so forth. But let's say for the sake of the argument that they are about 2 volts each. So 2, 4, 4, 6, 8. So the voltage drop through the LED is 8 volts. So how this work? So we start here, Negative, positive, positive. This is positive, and this go right to the negative side. So we do a Kirchhoff analysis of this will be 9 volts plus the current going through this resistor, that is IR, time, plus the voltage drop through each of them to 4, 6A, and then we return back to the negative, that will be 0. And when we do that, though, that means one important thing: if you have many of these LED in series to a point that is higher, the voltage drop through them is higher than the source, this circuit will not power the LEDs. They will not go anywhere. You have to have the source of the voltage here should have to be higher than the voltage, than the total sum of the voltage drop through the LEDs. Now, in this case, it's okay. I got minus I plus A. That's going to be minus 1. So that minus 1's go this way, and you have IR equal 1 volt. See? That will work okay. So I can calculate the value of R for this particular case. Let's say that the amount of current that I want through this, just through this loop, to have the LEDs sort of pretty well illuminated, we'll say, let's say 10 milliamps. If that's the amount of current, then the R will be 1 over 0.01 when you convert this to divide by 1,000. So that would be 0.01. So that would be about 100 ohms. See how easy? In series, there's no problem. That's 100 ohms resistor, but you can only illuminate 4 of them. See? This is how it goes. If I want to illuminate more LEDs, like adding 4 more LEDs, because you have to have the same voltage drop. If I add now like something in parallel here, you have to ensure that the voltage here drop, the voltage drop is the same as this voltage drop for this circuit to work. So I got 8 volt drop here. I have to have the same voltage drop through here. And the other stuff is just, remember, if you want to have 10 milliamp through here, 10 milliamp through here, that means that this circuit have to power with 20 milliamps. These are. So this is sort of like a combination between series and parallel. So you want to, I'm just want to stress the fact that the voltage drop when this is in parallel like that has to be identical. If let's say that the voltage drop in this side is lower because there's one of these LEDs, that is out of the bunch, you probably will light this up, this side, but this will be off because these have a lower voltage drop. So it will go right through here instead of this way. All right. I think with that say, guess that we are ready to go back to Tinkercad and do some more experiment. Okay, before leaving, one more thing. You can see here that it's about 10 milliamp, but not quite perfect. And I have here about 69.1. If you multiply 1, 2, 3, 4, 5, 6, 7 times 9.88. So the question is, why is not perfect? Let's see what's this resistor value. It's about 100. Makes sense. Let's check the voltage drop here. I assume in the calculation about 2 volts. So it's close, but let's find out what the actual value is. So we put an instrument. Remember, this instrument has to be put in parallel. Let's see what LED, what that voltage is. So it's voltage. Now I go this line. So this looks better actually. Let me get this a little bit higher. So this is the red one. I'm gonna test this one here. So it goes right to that positive. Now I go to the negative LED. Here we go. Oh, there we go. Here we go. There we go. That's the negative. So I got this one on the positive, and this one is right on the negative side. Okay, this one will read voltage, this read amperage for each LED, I mean at least one LED. This read the voltage in parallel, because which is interesting. I mean, when you read the voltage in parallel, all this will be the same voltage because they are all in parallel, and this will read the current of at least one LED. So you add up all the LED, that will be equivalent to what you are reading here, which is also in series. So you are reading the amps in series with this instrument. So let's start simulation again. There we go. It's not actually 2 volts. It's 1.98. I mean, close. We can keep adding more LED. Let's see. Let's add more. Copy. Let's add one more. Paste. Let's see. Right here. Copy. Paste. Copy. Paste. Copy. Paste. All right, good enough. Now this leg goes to the negative side, and this leg goes to the positive side. This to negative, easy to install. When you do this, this goes to negative. Oops. And this one goes to positive. Right, let's move it this way. Let's see, I got this one. This will go over this one, and this will go right here. All right, let's see how this works. Star. There we go. The current drop from close to 10, since I add more LEDs. And I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 LEDs. They are well lit. I mean, good illumination. What I could do, the voltage drop a little bit, but it's close to 2. That's why you get an approximate value for this resistor. I can drop this resistor, I mean the value. Instead of 100, let's say 50, and let's start again. There we go. I increase the current to 12.3 per LED, and the voltage kind of increase a little bit to the total milliamp that I'm pulling from the battery is about 136. Obviously, you are lighting more LEDs. There's a lot of energy being consumed at the battery side. Okay, I'm consuming 136 milliamps, and let's stop the simulation here and let's see the watts. Then put another instrument here and let's measure the voltage from this guy in parallel. So I'm measuring, let's change color here so that we get this done, and this is the amount of milliwatts that are being consumed from these 9-volt batteries. So start simulation. There we go. You multiply these two value, then you get the watts or the milliwatts that are being pulled by all this bunch of LEDs. And most important is you are consuming, like for example, batteries, the way they comes, they have amp hours. If you know the amp hours of these 9-volt batteries, then you will know for how long basically you will be able to power this circuit here, this LED, until the 9-volt batteries just drop to a point that is way, it's beyond the battery capability to sustain the circuit. But that again requires that you know the amp hours for this battery, because I know the current. And when you know the current and you know the amp hours, you basically can divide the amp hours by this amount of current, and you get the hours that the battery will last to sustain the circuit the way it is right now. All right, I hope now I can say yes, you pretty much got this wrap up. Like for example, you know how to set up LEDs in series, how to set them in parallel, and how to measure a bunch of add a bunch of instrumentation, so you know the voltage drop per LED, you know the current that is being consumed through one LEDs, you know the current that is being consumed through the sum of all LEDs, and finally you know the voltage that the battery is at. It starts at 9 volt, but when you are pulling energy, it starts to drop the voltage. And anyway, that gives you, if you multiply this by this, voltage by current, that gives you watts. But also, if you know the amp hours of this battery and you divide by the amount of current that you've been using on within the circuit, then you know how many hours will this battery will last to power the circuit. Well, now I'm done. Have a great afternoon. Thank you. Bye.